I don't.
Flying this morning, he said he was going to archive the talk today.
Yeah.
Archiving all of them.
Okay.
All of them archived.
Okay. I'll talk to him. Hi. Okay, we're on?
Yes.
Okay. Hello, everyone. Thank you for coming. It's a pleasure to have here Professor Ed Delp from ECE at Purdue University. Professor Ed Delp got his PhD from Purdue University, and he joined Purdue University after short tenure at the University of Michigan in Ann Arbor. He's currently a chair professor, the Silicon Valley Professor of Electrical Engineering and Professor of Biomedical Engineering at Purdue. He recently received a distinguished professor appointment from the Academy of Finland. This is a sort of a very prestigious Finnish program that they have with outstanding external faculty and researcher, and he's widely published, of course. He's served on many IEEE committees on communication, multimedia, information theory, and he's a fellow of IEEE, a fellow of SPIE, and a fellow of the Society of Imaging Science and Technology, a fellow. I guess I should have said I should have mentioned the
you
ones.
You can stop anytime you want.
The ones that he's not a fellow of.
Yeah, he's a jolly good fellow. You can stop whenever you want.
Okay. And he also received the IEEE Signal Processing Society Award for his image and video compression, and it's a pleasure to have him here. He'll be talking about some of his work in security, in multimedia in general. It's a pleasure to have you. Thank you.
Thank you.
The floor is yours.
Thank you very much. So, so I'm from Purdue University in West Lafayette, Indiana, a little town, a little bit smaller than your town. So, but it's sort of interesting. We have a little town. University is a little bit bigger than here. So if you can imagine this place in a very small town, that's sort of where I live. So I thought I would just start off very briefly and describe very quickly some of the work that's going on in my laboratory, just give you a quick snapshot of all the things we're doing. So I'm going to do this very quickly. If you want to find out more, you can visit the lab webpage, or you can send me an email or something like that. So we do a lot of work in video compression. We've been working in video compression for probably more than 20 years. A lot of interesting things going on in the area of video compression. We've also been looking at what happens if you sort of take video and transmit it through a noisy network. So we're doing work in error concealment. We're looking at video databases. In particular, we're interested in looking at indexing user-generated content. This is some work that's being sponsored by Motorola. In particular, we're looking at applying this to things like YouTube, among other things. We're also looking at problems having to do with location awareness, and lots of work in multimedia security and forensics, which I'm going to talk about. We've got work going on in video tracking and surveillance and medical imaging. We have some sort of an interesting problem where I'm sort of answering is, what is your data load? I'm trying to figure out how many, on an average day, how many bits do you actually touch and what you can do with that. We're looking at a lot of sort of local mobile applications, including some things having to do with image-guided navigation. We have a project on language translation, a sort of bizarre project on food and dietary assessment. I could talk about that offline or something. We're looking at problems having to do with content adaptation. What happens if you walk into a room like this and you have some content maybe on your mobile phone, and then you want to display that on a high resolution screen? How do you adapt the content for that type of stuff? We have a new project having to do with digital cinema. In particular, looking at some very interesting things having to do with color correction in digital cinema. And then we also are looking at applying social networking concepts to a lot of problems having not to do with social networking. So that's sort of what we're doing. That's about, hi Dev, that's about 14 PhDs worth of stuff. I always like to acknowledge people who are giving me money. So these are all the places in the federal government that I'm getting money currently from: the National Science Foundation and National Institutes of Health and the DoD. We also get money from companies. So we have a pretty good sized chunk of money from Motorola and Nokia and a couple other sort of bizarre places, and some money from the state government. So that's what used to feed all those graduate students. So I have 14 graduate students right now. And I'm actually looking to hire some more PhD students. So I'm actually here to maybe raid some people out of this place. If you're interested in maybe moving on, doing some. So it snows though where we're at, so you got to put up with that. So it's the good with the bad, I guess. Right?
Don't go there, too cold.
Okay. All right. So I'm going to talk. The talk is sort of split up into two areas. I'm going to talk a little bit about content protection because all of you maybe have ran into content protection, and I'm going to say a little bit about sensor forensics. I'm going to do the content protection stuff first, and I just want to describe some problems having to do with content protection. And some things that you probably ran into this if you use iTunes or something like that. There was a big thing in content protection that appeared in the newspaper quite recently. I don't know if you noticed this. Up until, I think, April of this year, Walmart.com was selling music. You could go to Walmart.com and buy, digital music. Up until April, before April, the music was all being protected by something called digital rights management, okay? And a couple of weeks ago, Walmart decided they're not going to support digital rights management anymore. So everybody who bought this protected content from them has to do something with it in another 2 more weeks. Otherwise, it's going to be no longer useful in their computer. They're actually going to turn it off. They won't be able to play the music anymore. And so you're running into a lot of problems having to do with content protection. If you buy something from iTunes or something like that, we're seeing there's lots of issues with content protection, and people are looking at, there's all kinds of weird things going on here. I'm not going to try to tell you whether downloading music is good or bad. I'm not here to do that, but what I'm going to do is I'm just going to talk to you a little bit about some of the research issues. People sort of say that content protection, there's like a loss of $30 billion worldwide. I don't know if I really believe that or not. If you sort of look at sort of content protection objectives, these are the types of things that owners of digital content say they want to do. They want to be able to protect their content. They want to be able to keep honest people honest, which I think is sort of a ridiculous term. And they want to be able to prevent things like unlawful copying and illegal access and a few things along that line. They want to be able to do things like do access control, who can copy it, who can control the content, how do you play it back, all the rest of this kind of stuff. This is analogous to like I think with iTunes, you can take music. How many people here use iTunes? Okay. So you can take the music, you can burn it, twice or 3 times or something like that, or there's some sort of rules on how you can use the content. You're going to see more and more of this. For instance, in February 17th or 19th of next year, we're going to turn off the analog television, and we're going to go to a complete digital broadcast. And there's been some discussion of something called the broadcast flag that content owners can put in the digital broadcast video that certain devices that you may buy, like a TiVo or something like that, will prevent you from recording that content. And there's a big controversy about this. So people are interested in sort of monitoring this. There's things like auditing. So let me just tell you a story. The Super Bowl last year when it was broadcast. Who here watched the Super Bowl last year? Okay, all right. So you probably watched it here. Dev, where'd you watch it at? Were you in town at the time?
Yeah, at a friend's house.
So you watched it at some local TV station here, right?
Cable. Yeah.
Cable. But it was broadcast, it was probably from a TV station.
Yeah.
I watched it, actually I was in Chicago at the time I watched it. There was actually 525 different versions of the Super Bowl broadcast on that day. Every TV station that broadcast the Super Bowl, and it came from TV station, whether you watched it on cable or not, actually put a different security features in the Super Bowl. So if somebody copied the Super Bowl and it later popped up someplace else, they could track it back to where the original content came from. Were you worried about this now, Dev?
More so than it was.
More so than you was at the time.
So they all have the same score?
What do you mean? Oh, yeah. The outcome of the game was the same. They didn't change that part. There will also be probably more than 600 different versions of the World Series broadcast. Well, the World Series starts in a couple of weeks or next week or something like that. There'll be 600 different versions of the World Series broadcast because every TV station will have different tracking technologies, in particular tracking watermark installed in the content. Now, part of the reason for this is that a lot of illegal American sports broadcasts show up in South America, and so they're interested in finding out essentially where it comes from. So you're seeing more and more of this. This is not necessarily meant for you to read, although if you want a real copy of it, it's meant to sort of overwhelm you. What you see here is every one of these entries is a copy protection system that you probably have run into. Now, about every one of these has also been broken, but some of them have been less so than others. One of the other ones you're going to run into is, as we move to this digital area, you might buy a device that has something called an HDMI output. That stands for High Definition Multimedia Interface output that you're going to plug maybe into your digital television. Okay, some of you are going to have trouble because when you connect that output to your TV, your TV may not recognize it. There's been lots of trouble with this because the security system on the HDMI, there it is, where is it? It was here somewhere. Anyway, the security system on that has lots and lots of problems. So for instance, if you, I don't know, who's your local cable provider here? All right, so Time Warner gives you a digital HD set-top box. It's possible that the HDMI content that comes out of that box won't be recognized by your TV. So there's all kinds of problems with looking at some of these security aspects. All of these systems have been broken, and a lot of these things you've run into. So as a user, what do you want to be able to do? Well, you want people to leave you alone. Okay, I say this all the time. As a matter of fact, I have a sign that pops up in my office from time to time that just says, "Leave me alone." Okay? You would like to make it easy to interoperate with things. In other words, take your content and maybe play it on your laptop or play it on your neighbor's laptop. You don't go out and buy a device that says, "I don't only want to play it on certain things." Content protection is not a feature. You would like to be able to do things like time shifting. In other words, record it at one time and watch it at another time. You'd like to be able to do format shifting, buy the audio CD and rip it so you can play it on your iPod. You might be able to do location shifting. This is like a Slingbox. You guys know what a Slingbox is. You sort of plug it into your cable TV system, and then if you're in China, you can log into your home network. If you have this set up properly, you can watch TV from your home while you're in China, okay? Some people say they want to do backups. I don't know. Do you guys routinely back up your DVDs? I don't know. Maybe you might want to do that. Guy in the back shaking his head. Now, I don't know if you have the right to redistribute the content to your 10,000 closest best friends. That's something I don't know about, so maybe you might want to think about that, okay? But these are features that people want to be able to do. Now, it turns out Hollywood doesn't want you to do this. What Hollywood wants you to do is they want you to, for every piece of content, they want you to buy it multiple times, okay? For every device you have, they want you to buy another copy. Now, if they had their druthers, what they really want you to do is every time you watch it or listen to it, you have to pay again. Okay? So think of like your TV like having a coin slot in it or maybe a credit card swipe. Every time you want to watch something again, maybe you have to pay. Okay? So these are some of the things people are looking at. Now, there's been all kinds of things have talked about how to fix this problem. There's technology, which it's not going to fix it. There's legal things. I'll say something about that. There's moral issues. Should we shame you into not stealing content? I don't know. Should we educate you that maybe... We okay? Yeah. Oh, okay. And then there's this question of should all content be free? Now, a lot of people think digital information like, you should be able to take and download music and all the rest of the stuff. Well, if you think all bits should be free, can I have your bank records? Those are bits, right? Okay. So let me just tell you a quick little story. I tell this to students. So I had the vice president for a large semiconductor manufacturing company in my office. And he was there talking about interviewing for students. I won't tell you the name of the company, but let's just refer to it as the Big I Company. Okay? Maybe you might think who that is. Okay? And he was saying, well, look, if people we're hiring now believe that information should be free, then what about corporate information? Should that be free? Should we just be giving that stuff away? Okay? Now, I had the executive vice president for research of a large software company. We'll call it the Big M Company, okay? And he was in my office, and he was also sort of asking the question about, well, what do we do about this bits being free thing? Is that something we need to be worried about? So maybe you might want to think about that, okay? These are all the laws that have been passed that try to keep you from doing things. The big one is the Digital Millennium Copyright Act, which does a couple of really bad things. Some people say it does good things, but one of the things it does that's bad is there's been a long history in engineering about doing reverse engineering. By reverse engineering, I mean you sort of take something apart and you see how it works. Okay? Like Ford always goes by the latest model of Chevrolet and they take it apart and see how it works. So, if you apply this to software and you sort of take it apart maybe, in a sense, if you're a good software engineer, you sort of figure out how it works. It turns out there are some people who believe that that's illegal, according to this. So reverse engineering, which has been a good thing for competition, may be outlawed in some interpretation of this law. The other thing I'd like to point out to you is this law down here, I always put this down here for the professors in the room. The professors believe, us professors, and there's some here in the room, believe that somehow they're exempt from copyright laws. That all I got to say is I'm using it in my class, and then therefore they get to be able to do whatever they want. It turns out that's not true. Okay, this law sort of tells you what rights you have if you're using it for education. And there's all kinds of other things you can talk about here. I just want to move on to look and talk about a little bit about the technology. And I'm going to do this very quickly, and we'll go on to something else. This is sort of the whole content protection system. Every time this applies to iTunes and applies to other things. You know, maybe you have some protected content. I'll say video, but it could be audio. You have some way of authorizing it. You know, here's Bob, who is a user. He has some sort of credentials. Maybe it's like a password. It says, I am Bob. He can play the video. All the rest of this stuff is unauthorized ways of being able to look at the content, including things like you could hack the device. Maybe you hack it so anybody can use it. You steal Bob's credentials, and then you can say, even though I'm Alice, I'll tell the system I'm Bob, and then I'll be able to get access to the content. So one of the most interesting one is this concept of the analog hole. In other words, you take the analog output and you just sort of redigitize it and you use it. However, many digital devices now, when they receive certain types of content, they turn off their analog outputs. So for instance, again, where I live, we have Comcast cable TV, and when they're broadcasting digital high-definition television, the set-top box turns off all of its analog outputs. And the only thing available to me is the digital outputs, which are encrypted, which means if I don't have an authorized device, I can't look at the content. Okay? And you're going to see more and more of this, where essentially you're going to go out in the future when we go to this digital television area. There's going to be more and more you're going to see the analog outputs are going to be turned off, or they're going to be switchable so they can be turned on and turned off. All right. So this is sort of the overview. And again, I just want to hit a few things because I want to tell you about there's lots of interesting research here, and it's not all of it is bad. I'm not saying we're just trying to, there's some really interesting problems that can be applied to a lot of other things. But this is sort of the idea of how you control access to content. You need all kinds of things like a secure packaging. You need some sort of rights expression language to tell you what you can do with it. And then you need ways of sort of binding this, the conditional content, or the conditional access information to the content. And then there's all kinds of other things about tamper-proof devices and a few other things. Here's some interesting things from a research point of view, and that is renewability. If you have a security system that you field it and you have tens of thousands of users using it and it breaks, how do you fix it? Now, one way to fix it is to have everybody send the devices back to you. You fix the devices and you send them back out. Another way to fix it, if it's very software-oriented, like what iTunes does, what Apple does, if iTunes gets hacked, what Apple does is they immediately shut off access to the iTunes store until you download the newest version of iTunes. Okay? So what Apple will say is there's a new version of iTunes, you can play the content you have now, you just can't buy any more content from them until you update your software. So that's another way of doing it, is sort of pushing out new versions of the software. That's okay for a software-based device, but what if it's a hardware-based device? It's purely a hardware-based device. What are you going to do? Are you going to tell people they have to connect it to the network? So, for instance, if any of you went out and bought a Blu-ray HD DVD player, you'll notice that those devices all require either a telephone connection or they require you plug it into your home network. Why? So then you can download firmware patches into it in case the thing gets hacked, and it has been hacked once. Okay, and if you don't update it, then future DVDs you won't be able to play. Okay, so there's this issue of authentication, which it's going to come back again and again. Okay, and there's all kinds of other things like, what about errors, and what about how does it work with the compression method? These are all really, really neat research topics. If you're a graduate student and you want to do something that sort of combines signal processing, let's say with security, there's lots and lots of interesting things here to do as far as the research topics are concerned. Now, as users, these are sort of, I'm going to go through these quickly, these are sort of the things that users would like to be able to do. They would like to be able to have, they don't want the system to violate their rights of privacy. In other words, they don't want the device to spy on them. And I'm going to show you an example of a device that we've actually made that spies on you. And I'll show you that a little bit later. They also don't want whatever the security system does, they don't want it to damage their device. So were you guys familiar with the Sony rootkit system? Did anybody know about that? Some people are shaking their heads. So here's what happened. Sony produced, I think it was an audio CD, that you sort of loaded it onto your system, and if your computer system, and then it came up and asked you if you wanted to download some software. Now, I'm sure all of you, when that little thing pops up, it says yes or no, you all sit down there, deep thoughts read it, right? So people said yes, and when you said yes, it installed some nice software, but it also installed a rootkit. Now, what is a rootkit? It's something, it's not like a virus. It can't be removed by virus protection. And what it basically did was it allowed Sony, whenever you played future content, to turn off certain features of your player. Okay? And maybe that's not a bad thing. But what the other thing is it did is exposed your computer to hackers. Okay? Now, Sony there was a big lawsuit over this. There was a bunch of other things going on. And so they ended up having they had to pay a lot of money. And so you can run into some problems. Okay, so these are sort of what users want. Again, the tool set. Well, you can do authentication or encryption, authentication. You can do hashing, timestamping. I'm not going to have a lot of time to go into these, but I'll say a little bit. Maybe you know about encryption, but maybe you don't know about authentication. Now, authentication is answering the question, are you who you say you are? Okay? Now, how many people have flown in an airplane? Raise your hand. Taken a trip. Okay? What do you do when you go to the airport? What's one of the first things you got to do? ID. You got to cough up an ID. So basically, you have a physical piece of paper or some physical thing where you're sort of authenticating yourself. Okay? And so you're basically telling these people, this is who I am. All right? Now, there's a great cartoon, which I couldn't find, that was appeared in the New Yorker, and there was a picture of a dog typing on a computer. And the caption said, on the internet, nobody has to know you're a dog. Okay? So the first question I always ask students is, when you get an email from somebody, how do you know who sent it to you?
Name.
It says from somebody like that. Do you know how easy that is to fake? Okay? So here's an experiment you can do. If you have access to an email system, if you can send an email to yourself, then I could show you how you could send an email that looks like it comes from anybody you want it to come from. Okay? But I'm not going to show you how to do that. But I could. Okay? So if you have really, really secure systems, you shouldn't be able to send emails to yourself, or it should flag it if you try to send emails to yourself, because you can fake it to make it look like it comes from somebody else. And then you get into all kinds of issues of permission. But here's a more important thing. How does a physical device authenticate itself? Okay? When you take a picture, maybe with a camera, how do you know maybe that picture, or somebody says, here's a picture I took with my camera. How do you know that camera actually took this picture? If somebody says, I printed that document on the printer in my office, how do you know that did that? How does a physical device authenticate itself? I'm going to say something about that later. These other forms here are different types of authentication. This one just says, I created something at a particular time. Now, you may say, well, wait a minute, I can take my computer and I can change the clock. Yeah, I'm not doing this. We're doing something called a third-party trusted entity who's telling us what time it is. And then there's watermarking. I got to get going. So here's the issue of encryption. And there's all kinds of interesting things having to do. One thing I'll point out to you with encryption, here's a good research project for you. How do I encrypt data and decrypt it in noisy environments? Because encryption is very fragile. If there's any noise in the encrypted information and I decrypt it, I get junk. So this idea of doing error-resilient cryptography is a really important research area, and it's a really, really hard problem. So if you can come up with a really good way of doing it, okay, you can make a lot of money. Okay? I'll tell you right now, all the banks would buy it. Well, if there's any banks left, all the banks would buy it, okay, and things along that line. There's also lots of other issues having to do with how do you, encryption is really made to protect all of the content, and it just treats bits as bits. How do you sort of encrypt something that maybe is specifically related to audio or video or something along that line? Here's watermarking. Maybe you've heard about watermarking. What watermarking means is you insert a little bit of controlled distortion into an image. This is what the watermark looks like. It's sort of hard to see. Maybe on your monitors you can see it a little bit better. And what you can do is you can essentially use this to sort of hide information. This is sort of what a watermarking system looks like. Again, if you know something about information theory, for some of the people maybe in the audience knows something about information theory, this is a channel coding problem with side information. And there's lots and lots of research we've been doing. We've been working in this area for about 10 years. As a matter of fact, we've developed this test system. It's called the Watermark Evaluation Testbed. WET, Watermark WET. You get it? You get it? This was developed for the Air Force and is now used as part of the National Infrastructure Testbed at the Air Force Research Labs. One other thing, maybe you've heard about steganography. Okay, so this is an example of this message that you see in typewriter font is actually stored in this image. And it's stored actually it's mixed in with the pixels. And you really can't tell much difference between these two things, particularly if you only see this image. You can't tell anything's hidden in it. Now, steganography's been around for a long time. It comes from the word steganos, which means hidden, so it means hidden writing. So one of the first steganographic systems was there was a Greek general who wanted to send a message to another general, and he wanted to make it be secure. So he took the messenger's head, he shaved his head, tattooed the message on the guy's head, waited till the hair grew out, sent him on his way. On the other side, they shave his head and read it. So it's sort of a low bandwidth communication system, but it worked. Okay, and there's been some talk that maybe terrorists are using steganography systems to actually transmit information. And this particular tool, it was this particular tool that was used at S-Tools 4.0. I actually helped put somebody in jail who committed a crime using this tool, but I can tell you that another story if you want. So let's talk about sort of the problem of authentication. All right. So you have a source that wants to send data through an insecure channel, and maybe you have a user over here, and you have an attacker that can maybe sort of attack the data. Maybe they can change it or something like that. And maybe you want to ask the question, what is this device that's sending this content? Now, the way you do it in a classical system is you have an authentication channel that actually asks in a very strong cryptographic way, this user that wants the content from this source, is this user who the user says it is? Now, the problem with this is it requires a backward channel. Okay? Now, you see this every time you're browsing on the web, and you know that little key locks up on your browser? Okay? You've essentially built an authenticated, secure communication channel between you and your bank. Now, let me also warn you about something. How many times you've been to a website where they ask you to accept a certificate? Okay? Do you automatically say yes? Okay? You shouldn't say yes. If you say yes, you could essentially let yourself open to something called a man-in-the-middle attack. Okay? So here's what I do. When they offer you the certificate, they also offer you a signed hash of the certificate. I then take that and verify that with the certification authority that it's valid. Otherwise, you can get into trouble. So don't always be answering all those damn questions yes. Okay? But this is a problem. For your bank communications, there's no problem. You're on the internet, a two-way channel is okay. But what happens if this is not, you can't have backward communication? How do you do the authentication? Okay, and this is where we're going to get into device forensics. What we're going to do, I'll give you a preview of coming attractions, is we're going to look at how this content is made and argue that it might be self-authenticating. Okay? So let me show you what we're talking about. So, all right. So you got all kinds of things that are available these days. Computers, cell phones, printers, digital cameras. And you have sensor networks and digital images and all the rest of this stuff. The question is, what can I do to be able to trust the output of a device? In other words, if I want to say to you, here's a JPEG image, tell me which camera took the picture. Now, there's lots of applications for this. Okay, that's one application scenario. So what we're actually interested in doing is we're actually observing the output of some sort of device and then answering the question, which device produced it? And this is the area of sensor forensics. Now, it's not like CSI forensics because those guys don't understand this problem. Okay, but it's the idea of being able to sort of authenticate that the data you got you can trust. Okay, and this is sort of a big research area. All right, so what you're going to do this, and I'm going to show you 3 examples, sort of 4 examples actually. You sort of exploit the way the device makes its output. Okay, so what would you like to be able to do? Maybe you could identify the device type, the make, the model, or maybe how the device is configured. Or you might want to even ask your question is, can the sensor be trusted? Here's one of the things that's going to happen in the future, in the 22nd century. The biggest thing is going to be trust and trust mechanisms. The issue is going to be you would like to be able to say, can I trust somebody and can I trust something? Now, when you trust somebody, you're going to do things like maybe have ID documents and things like that. But how can you know you can trust something? Can you trust your camera? Can you trust your printer? Can you trust your computer? For instance, can you trust that your computer is not, as you're typing, sending all your keystrokes to somebody in Russia? Because your computer has been made part of a zombie network. Because you accidentally downloaded a file or you answered yes to one of those messages. Or you opened up an email attachment. Okay? There's an estimate that says that 40% of the PCs in the United States have spyware on them, and of that 40%, maybe as many as 60% of those are connected to zombie networks. And what does a zombie network mean? It means it's controlled by somebody who can make it do something. So what could it make it do? Well, here's an example of one of the things it could make it do. When Russia invaded Georgia, or parts of Georgia, all of a sudden all the Georgian websites went down. Why did they go down? Because some hackers in Russia basically told probably about 100,000 zombie computers, some of which in the US, to all do denial of service attacks against Russian websites. Okay? So how many, besides maybe having virus protection on your computer, how many of you people worry about spyware? How about if you worry about it? Well, you're probably required to.
Yes.
Okay. What about things like keyloggers? What's a keylogger? Where somebody can record all your keystrokes and send them off to somewhere. Okay? So there's issues there you might have to worry about. So the question is, how do you know you can trust things? All right? And then there's issues having to do with forgery and altercation, and there's even things like fingerprint and trace. Now, there are some downsides to this, because if we can answer this question, then we can also make a device that can spy on you. Okay? So, what we're interested in doing in this research is we're interested in looking at 2 sides of things. Intrinsic signatures, in other words, something that's intrinsic with inside the device. We can also do things like extrinsic signatures, where maybe we modify the device excuse me, so that it can actually put this tracking information in there, and then there's all kinds of things we can talk about intrinsic and extrinsic. This is what I've done in my laboratory. We've done printers, cameras, scanners, sensor nodes, and RF devices. Okay? So, here's an example of one forensic technique we've developed. Here's the original picture here on the left, and what I did for the kids is I flipped their lips. You notice that? And I changed the background. Okay? Now, with only knowledge of that picture and using some techniques we developed, we can determine that's where the image has been altered. Okay? Now, this is using something called an extrinsic tracking watermark that is embedded at the time the image is acquired. Okay? And to hack this would be very difficult. But this is one area of looking at forensics where you might be interested in, has somebody modified my content. Okay? So, you know, in the old days, people used to think of photographs as being fossilized light. Digital images are way too easy to manipulate. What do people call it now? They're photoshopping it, right? Now, one of the persons who's been the most victimized of this lately is Sarah Palin. There are some absolutely disgusting pictures of her, all of which are fake, that are appearing on the internet.
Some of them are real.
We actually have a project right now where one of my PhD students is collecting these images, and we're doing tests against, and we've not found any of those provocative images as being correct. Now, everybody thinks this is a joke, but you wouldn't think of it as a joke if these pictures were of your sister or your wife or your girlfriend or your mother or something like that. Okay, so you can go to this website, www.sensor-forensics.org, and you can see all the stuff that we're doing. And I'm doing this with a couple of my colleagues, Jan Allebach and George Chu, and we're looking at a lot of different things. Let's talk about digital cameras. One of the things that you can exploit in a digital camera is that when you take the picture, whether the device is a CCD device or a CMOS device, there is something in there called sensor pattern noise. Okay, and it's related to sort of dark current inside the sensor. And that sensor pattern noise is inherent to the sensor, the imaging sensor inside your device. And if you buy two cameras of the exact same model that were made on the exact same line, they're going to have two different sensor pattern noise. They're going to have two different noise patterns. You can collect those noise patterns by doing some test images, and then you can use that to identify an image taken with that camera if that image pops up later on. Okay? And there's lots and lots of details we can talk about this, but you can talk about how this pattern noise is sort of, you can think of it as a reference pattern, or basically it's an inherent watermark or a signature that the device tells you where it is, okay, or what it is, all right? Now, you may say, okay, let me show you the next picture. Whoops, go back. So this is sort of how the system works. If I have a collection of these sensor noise patterns, now I'll say something about the collection. I take an image. What I do then is I do some signal processing operations that are related to some very stochastic denoising operation. It has a big name. All this stuff has big names, okay? So some sort of signal processing thing we do. And then what we do is we sort of do a correlation operation and some pattern recognition, and we can tell you which camera took the picture. Okay? Now we say, wait a minute, how are you going to do that? Well, when the camera is manufactured, it's possible I could have the manufacturer, because when the manufacturer builds the camera, they take several test shots anyway to make sure the camera works. I could collect the sensor pattern noise at that particular time. And then maybe I could have a central location where I collect all this sort of forensics information. Okay? Now, I'll give you a hint where maybe this location is. It's in a place in Virginia called Quantico, Virginia. Okay, some people in the back room are smiling. Does anybody know what I'm talking about when I'm referring to Quantico, Virginia? It's the FBI laboratory, okay? And so you may say, well, then how do they know that that camera belongs to me? Well, let's say you go buy that camera at Best Buy's. And when you go buy that camera at Best Buy's, you pay with a credit card. And what do they do when you buy the camera at Best Buy's? First thing they do is they scan the barcode on the box. And what does that barcode have in it, among other things? The serial number of your camera. So now they got the serial number of your camera tied to you. They say, well, I gave it away. Well, that's fine. They'll come talk to you first. And then you can tell them who you gave it to. Okay? And so this would be very easy to do, and actually it's done. In my lab, we have, I don't know, 500 or 600 digital cameras. You know, if you come to my lab and you sign some documents and you're nice about it, we'll give you a digital camera you can play around with. You just got to give us some of your images and stuff like that. So everybody can get a digital camera. My students have lots and lots of digital. So come visit me, we'll give you a digital camera. I mean, you got to eventually give it back to us. But so you can, okay, so you say, what about hacking? Well, we could go over this. You know, maybe you can post-process the image. We can get around that. There's all kinds of anti-spoofing or spoofing techniques you can try. We can also get around that, all right? So so the issue then becomes, well, how could this be used? Well, there's law enforcement applications. There's terrorism applications. There is also some privacy issues here, because what this says is that every time you take a picture with your camera's spying on you. Okay, so we'll talk a little bit more about that. We've also done this with scanners. And with scanners, it's a little bit different. It's a little bit more complicated process. But again, the image is you scan the image. We can tell you which scanner took it. But not only that, we can tell if the image came from a digital camera, you printed it, you rescanned it. We can tell you the camera, the scanner, and the printer. Or the camera, printer, and scanner. We can do all of that, because those are counterfeit attack scenarios. So we can do all of that, okay? So actually, this was some experimental setup. This was some original results. I just want to show you some quick things. So we got 100% accuracy on the classification, very high. So right now, I don't know, we have like 400 scanners. We take lots and lots of data. You know, you come to the lab, you're really nice. We'll maybe give you a camera and a scanner. And if you're really, really nice, we might even give you a camera, a scanner, and a laser printer to take with you, because we got lots of those too. So we're collecting lots and lots of data. I drive the people at the university nuts, because not only do I want to buy new scanners, I want to buy old scanners. So my graduate students that work in my lab are authorized anytime they see an old scanner somewhere, they can buy it as long as it's less than $100. Okay, they can buy as many as they can get. So one of my students actually ran into some place in Columbus, Ohio, and he bought 100 scanners for $20 a piece. And we got this in the lab, and we were using them, and they were really old. And some of them didn't work. We had to fix them and things like that.
This is not in China. This is in Indiana.
He bought in Columbus, Ohio. He was in Columbus, Ohio. He was visiting his brother at Ohio State University. We can also do this with printers, okay? Now, one of the reasons why we can do this with printers is so my colleagues are world-recognized experts in printers. So if you have bought an HP printer, not a document class printer, but the kind you might buy for yourself, since 1994, it has Purdue technology in it. Okay? Now, that's stuff I did, stuff my colleagues did. So we can combine their expertise in printing in sort of my expertise in security, and that's what we've been doing. This project actually has been funded by the National Science Foundation to look at various problems and how do you take the output of a printer and identify what the printer is. We can do that. And what we're doing here is we're exploiting, again, essentially quality defects in the printer. How the printer actually puts marks on the paper, that tells us who printed the document. And I'll show you some examples of this in a second. I actually got some printed documents in my case. One of the things we exploit is something called this banding phenomena. This is what the inside of a laser printer, and by the way, I'm using a colloquial term here. When I hang around with printer guys, it's not a laser printer. It's an electrophotographic printer. Okay? So if you want to impress your friends, you can tell them you have an electrophotographic printer. Okay? Because when I hang around with these printing guys, they say laser printer. They say, what are you talking about? It's an EP printer. It's an electrophotographic printer. Okay, so this is what an electrophotographic printer looks like with all these gears and everything in here. And so it's a real mechanical engineering problem where these gears don't mesh and they try to flop around and things like that. It's moving. And what this does is it generates so-called banding noise in the output of your document. Now, most of the time, you will not be able to see this. If there's a real problem, particularly, let's say, your laser, I'll use the word laser, your laser printer cartridge is really, really getting old and you're sort of pushing it, you know, to get that last little bit out. When you print something, you might see this banding pattern. That's when you get really, real low frequency terms. But most of these are high frequency terms. This is cycles per inch along here. These things essentially are a signature that give away the printer. Okay? They're unique to the printer. Now, if you want to ask me the standard questions, I'll go ahead and get them before you answer them. What about changing the paper? We've done that. Changing the ink? We've done that. We've even done this, something similar to this with inkjet printers. We can change the ink. We've even, you know, you can buy gold and spray it using an inkjet printer. You want to buy gold ink, real gold ink, you know, 14 karat gold ink. You really impress your friends. You know, you print something about this big, it costs like $30 or something like that. We've done gold. We changed the paper. How about if the thing's old? We've tested this on printers that had something like 20 million impressions have gone through them. We can combat all of that, okay? So let me just show you, we've been able to do this based on some texture analysis of using that banding pattern. This is sort of a quick view of it. We basically scan the document, so we have to take the document and rescan it. Now, this scanner is a cheap scanner. It's a $150 HP scanner, so it's not a big deal. Scan it at 600 DPI. And then what we do is we sort of extract things having to do with certain letters. And again, I don't have enough time to to do this in great detail. But what we can do then is we can then identify the printer based on looking at those types of features. Okay, and we can map this back, and we've done this with all kinds of printers. For those of the faculty members here, you'll like this. My department head loves me because we supply printers to our business office, to all the secretaries in the department. All they have to do is once a week, they have to run 14 test patterns. And so anybody that wants a printer can knock on my door. We'll give them a printer. They may not get a new one. They may get the one that has 2 million copies have gone through it. They'll get the one that we need the data on. And we even give you the cartridges because we want the cartridge material back. And so we got hundreds and hundreds of printers, okay? We've also been able to do the extrinsic problem, where what we do is we exploit sort of the edge raggedness in the printer, and we can actually treat this as a digital communication problem, and we can actually embed information. And let me show you an example of this. I got some things here I can show you. Unfortunately, for the people at the remote site, I can't show you this. I'm going to give you an output now. One of the things, you can try reading this, okay? It's going to look sort of like English, but it's not going to read right, because this is generated something called the forensic monkey generator. Now, what's the forensic monkey generator? It goes back to the problem that says you give 10,000 monkeys typewriters and eventually they type Shakespeare. Well, we've sort of given 10,000 monkeys typewriters and they type Sherlock Holmes. Okay, now the reason why we do this is we can control with a high degree of accuracy what the probability density function of the letters is on here. If you get the one that has nothing, that is an original, okay? If you get the one that has a 0 on the back, you should probably do these side by side. Let me see. I don't know. Here it is. This one has 400 bits of information hidden in it. Okay? So we can put 400 bits of information in a printed document. So the one, if you turn them on the back, there's one that has nothing on it. That means there's no. Oops. Did I give you the wrong one? Oh, hold on. Oh, X is nothing. Give me this one back. So the one that has X on the back means there's nothing embedded. The one with the circle on the back implies there's 400 bits of information in it. We can extract all that 400 bits of information back out with a very high probability. And again, we can model this as a digital communication system. We can hide this information. Now, I should also point out to you, we're not doing this by hacking the print driver. We're doing this by modifying the way the laser voltage inside the laser printer actually works. So you're not going to be able, unless you're you know a lot about printers, and you want to take your printer all the way apart, you want to modify the laser voltage, you're not going to be able to hack this. You can't get at it through the print driver. So it's a very, very secure system. And we can hide all kinds of information. So, again, what could we do? Well, when you send something, you know, one of the things maybe you don't realize when you print something like what Microsoft Word, Uncle Bill, there's a lot of things embedded in your Word document, right? Including usually your name and a bunch of other things. Well, that information could be passed to the printer and we could embed that in here. And there's a bunch of other things we can do. When you turn your printer on, maybe you don't realize it, you start a clock up. Okay, and we can interrogate that clock. Why is that clock there? That clock's there for warranty information. So you think you're going to fake HP out and say your printer's broken and I got a fake certificate about when I bought it? All HP does, as soon as they get the printer back in, they interrogate the clock. If the clock's been running longer than your warranty, they said this thing's out of warranty. They won't fix it. So you can take a look at that as it's being passed around. Okay, the last thing I'm going to talk about is RF circuits. And this is something I do with Professor Steer in the back and Deb Palmer, who's in the back. Here what we're trying to do is we're trying to ask the question, can we maybe identify an unknown RF device by maybe sort of listening to its output, okay? So one application of this would be, let's say you roam into an area and you want to ask yourself the question, is there any like Bluetooth devices or 802.11 devices? Because according to the FCC rules, those are unlicensed spectrum, the FCC has a very strange rule. The rule says you cannot interfere with people, but you must accept interference. So maybe what you might want to do is come into some area, maybe see if there's anybody out here you might interfere with, and then maybe you might not want to do something, okay? So that's an application. So we're interested then in this particular problem, which is funded by the Army Research Labs, and here's our web page. And there's a bunch of universities, Duke and University of Illinois, and there's Purdue down here, and there's all the people working on it. Professor Gard, also from NC State, is also working on on the project also, and several of the graduate students in here look like they're war weary. Would that be a good way to describe you guys? You're getting there, okay. Ready to graduate? All right. So the project's very complicated, but my sort of part of it is simple-minded in the sense that the idea is you have some sort of device, and maybe you transmit a very low-level probe signal. That then goes into the device, and you can show that it will be re-radiated back out because of certain nonlinearities and other things inside there. Then you want to be able to essentially measure that return signal, probe signal, extract some features, and then classify it. Okay, and so we've been working on this problem for a long time. We're worried about the front end, like the antenna, the filter, and maybe some nonlinearities, usually typically in an amplifier generically. Maybe there's some diodes or something in there. And so we've been looking at this problem of designing what types of probe signals you need to do. How do you then process the reflective signal that comes back? We've been doing a lot of things in this area. For instance, we've been looking at chirp signals, because chirp signals have what is known as very high time bandwidth products. What this means is for a relatively low amount of energy, you can have a very broadband signal. Okay, and the idea is to put this sort of energy in there and then get all this energy spread out across the frequency. So a chirp signal basically is a signal that sort of starts off at a lower frequency and then ramps up to a high frequency. And then this one actually ramps back down. This is called a back-to-back chirp. There's also sort of, it shouldn't be, that word regular shouldn't be there. It should be just a regular linear chirp signal. We've done a lot of work in this area, including some interesting theoretical work on actually analyzing the frequency of this signal. And actually we've developed some really, really interesting techniques. A student of mine who's now graduated and working for the Army developed some really interesting techniques for actually analyzing this signal in more detail. I don't want to bore you with that. And this is the only equations in here. So, okay, there's a couple equations describe what a chirp signal looks like. And so what we're doing here, and this is I already told you what that is. Okay, let's keep going. So what happens is when you sort of input this signal into the sort of the RF device, you can sometimes maybe get some very interesting phenomena having to do with the passband or near the passband of this particular broadband filter. And these little ripples up here and some of the ripples down here, we believe, and based on some experiments actually done here at NC State, we believe those things actually characterize the device, and then we could actually say what the device is. Okay, so we've been looking at all kinds of features having to do with bandwidth, center frequency, filter response, and lots of stuff. If you want more detail, you can talk to Professor Steer, or you can send me an email. We can send you some papers to read and stuff like that. So one of the things we've been doing is looking at these sort of chirp features where we're actually looking at the power spectrum in the response and then using these as so-called measurements that are part of this basically then forms the signature of the RF device. And then we can classify the RF device based on that signature. I'm going to stop here. There's lots of neat research problems. There's also a very important problem I didn't talk about, and that is a privacy problem. What happens is all of this device forensics it can impede on your privacy because we can make devices that can spy on you. Okay? So for instance, one of the things that could happen is, let's go look at the RF problem. Maybe you're there using your computer and we come in and sort of evoke our probe signals. You may not know they're there. And we figure out that we're getting a response from some sort of Bluetooth system. And we can figure out that Bluetooth system maybe belongs to Professor Hamid here. And then we can figure out he's sort of in the room, and what's he doing in here? Maybe we're at some weird place that maybe you shouldn't be, or maybe you shouldn't be. And so we can actually use this to essentially spy on people in ways that maybe you're not aware of. So there's all kinds of interesting things here. In general, what this is sort of a merger between security, classical security approaches, and signal processing. So I think I'll stop here. I've probably gone longer than I want to, and I'll be more than happy to answer questions if anybody has any questions. Thank you.
Time for questions.
And that stuff is still being passed around. If you, I don't know where it is. Did it make it back there? It's coming. Okay. Any questions? There's one up here, I think.
Yeah, in the security arena, do you prove theorem like in a signal processing area?
You can, in regular security, you can prove things that are, you can show using Shannon's information theory that things are provably secure. Yes, you can do that. As a matter of fact, Shannon had a test for security and for a system that's absolutely secure. And what it boils down to is, now this is a security system, not one of these forensic, not one of these things we're doing. But for a security system, it boils down to something that's referred to as a one-time pad. And what you do is you use Shannon's two measures from information theory called equivocation. One of them is called equivocation, and the other one is called, well, it's sort of related to channel capacity, but it's not channel capacity. And you can use these if you set the problem up to show that something is provably secure. And the classical example of that is a one-time pad. A one-time pad is provably secure as long as you only use it one time. Okay, that's why it's called a one-time pad. And there are some banks, particularly in Europe, that are using one-time pads now they're a real pain to use for users.
A question about you called it banding for the printer identification?
Yeah.
Even though it's based on a mechanical gears, it doesn't degrade or change the signature over time?
No, we actually there are some parts of the banding pattern that do, but there are some fixed parts of the banding pattern that do not. That's a very good question. That's a very good question. And we know which parts of that we need to be at. I'm sorry, go ahead.
What if you modify the printer and run it at faster than it's known to run?
You know how to do that?
Just change the motor, right?
I change the motor, then probably the printer won't work.
Yeah, and the code.
Yeah, it won't work. We know a lot about printers. That dog won't hunt. So, yeah.
Yeah, I have a question. It seems to me that you're using the noise patterns of the camera or the printer as this fingerprint of the device.
Right.
So, did you test that whether this fingerprint are invariant to your environment, say temperature, or maybe you're shaking your printer while you're printing something?
Yes.
Can you change that?
Yes, you can't change it. We've tested all of that. I've been working on this problem for a long time. No, you can't.
It's like you can cheat. You can cheat.
It's very hard to cheat. There's ways of cheating. I know how to cheat too, but we're not publishing the cheats.
Okay.
So there are ways of cheating, but that's not one of them. So we've looked at all this. I mean, I got there's like 7 PhD students working on this part of the stuff. So we've been working on parts of this stuff for more than 10 years. So yeah, you can't. It's difficult. Okay, and I mean there are ways of doing it, but it's not as easy as you would think. Okay, now does that mean that people can't do it? I mean, there are ways of still fooling it, but the problem is that, say if you use a camera to commit a crime, this is not the only thing that's going to convict you. This is going to help more in the investigation than it is going to be in anything else. So for instance, I'll give you a scenario. Let's talk about a counterfeiting scenario, okay? By the way, okay, here's something else. Here's a little message to the students from the U.S. Secret Service, okay? Now, maybe you heard of the U.S. Secret Service, that they guard the president. But the other thing the U.S. Secret Service does is they worry about counterfeit money. It's not the FBI, it's the Secret Service, okay? It's been that way for a long time, more than 200 years, well, more than 100 years. Okay? Secret Service comes and gets you, you do counterfeiting, all right? So one of the problems that happens every year at various universities is that the students go out and have a good time on a Friday night, and they come back and maybe they've had a little bit too much alcohol. And then the guy has a really nice color printer and he has a really nice scanner, so he prints a $20 bill. Scans it, prints it. And then as a joke, you go pass it. Okay? You should know it has been the official policy of the United States government since 1904 that there is a zero tolerance policy on counterfeiting money. Okay?
Except if you're government.
Wait a minute. If you counterfeit any money, the U.S. attorney, which probably there's one here in Raleigh, I guess, probably for the Eastern District of North Carolina, is going to come at you as if the same thing you counterfeited 100,000 of those $20 bills. Okay? And what they're going to get you to do is they're going to say, we will agree because you only did one. You plead guilty to a counterfeiting charge and we'll get you no jail time. Oh, that's fine. You say, that's good. But you just pled guilty to a Class 1 federal felony. So then you go apply for the job. Have you ever been arrested? Well, yeah, I have a Class 1 federal felony. I didn't go to jail, though. Well, what'd you do? Counterfeiting. Oh, yeah, we want to hire you. Okay, so that's my commercial. Don't do it. Okay. Now, the question the question had to do with having to do things like the counterfeiting attack. In the counterfeiting attack, what people are more interested in is finding out what was the printer that we used to print the money. Okay, so they don't necessarily care it was your printer. What they're interested in is saying it's an HP MP4, okay? And then what they can do is they can then get a judge to issue a warrant to be able to search your house if they suspect you to see if you have one of these printers. If you do, then they're authorized to essentially seize the printer. And if they seize the printer using our techniques, they only have to print 4 documents to absolutely say you're the one that did it. So in many ways, it's not like some hand's going to come out from the sky and pull you out of the, but it's good as an investigative tool. And there's all kinds of other things you could potentially use this thing for, particularly with a lot of these fake images. For instance, if somebody says they took a picture of our vice presidential candidate and she was dressed in a certain way, it's very easy to show that that picture never really came from a digital camera. It came out of Photoshop. That's easy. It's easy to do. So any other?
In theory, we could use that to catch bin Laden.
I don't talk about that problem. Okay? Is there any other questions? Yeah.
Are there Photoshop techniques to add random noise that destroy the correlation to a camera?
Yeah, it doesn't work.
Okay.
Yeah, because the correlation is not just random. So there's actually a pattern in there that you can actually, it's very hard to destroy the pattern. So this is a hard problem. Now, does it mean you can't do it? I mean, yeah, there are tools, there are spoofing techniques, but again, we don't publish those. So there are spoofing techniques. So, yeah. And I think you're going to see more and more of this sort of use. And there is, the privacy thing is an important thing because, you know, you have a right to be left alone. I mean, there is certain rights of privacy that you have as a citizen. And so the idea of somebody using this to sort of track what you're doing there's some worrisome things. We actually are working on a project now where we can actually, for the printers, we might be able to do things like turn the intrinsic embedding off. And we've actually have a little proposal in to be looking at that. So we'll have to see. So, yeah. But we can, yeah, I mean, the printer, people don't realize these devices. And you can do this also with a couple other things. There are other types of devices. You can also do this with things inherent to your cell phone, not just the RF or the camera in your cell phone. Even inside your cell phone, you can look at patterns the way people do things. Like if you do a lot of text messaging, it turns out you can look at the patterns on the way people enter text, and you can sort of tie that as a forensic tool to. And how you can do that is that a lot of the newer cell phones have accelerometers in them, and you can capture that information through the accelerometer. So there's all kinds of ways. Well, you know, your iPhone has an accelerometer, and all the new Nokia phones have. And they're made, you know, you think they're used just so when you turn the cell phone this way, you know, but it actually can. It actually tells you that what is known as the pose of the device, you know, how the device is being held and how it's being moved. And you're moving it as you're doing the text messaging, and so we can get that signature out too. There are ways of doing that. So.
All right. Well, if there are no more questions,
Well, now I'm just.
let's thank us.
Thanks. So I guess I should turn this off.